Computer Science 461. Everything you wanted to know about formal methods but were afraid to ask. So, let's see a gentle introduction to formal methods, and I have quite a few formal methods cartoons for the lectures that we'll have in this module. They're not tremendously funny, but formal methods aren't tremendously funny anyway. So, what are these formal methods? Basically, formal methods use mathematical notation to describe required properties of an information system. For example, in Z, we use mathematical data types to model data, and we use predicate logic to describe the effects of operations on our systems. Formal methods describe what the system has to do without saying precisely how it'll be done. So it leaves the code up to you, but it says exactly what the system needs to do. So they're independent of the program code itself. So why am I going to talk about Z? I'm a fan of abstract state machines. This is maybe an argument that someone in grad school might make. But Z, and it is pronounced Z because it did come from England, is the formal method that we'll be studying in this course. Z was developed by Jean-Raymond Abriel in the 1970s at Oxford University, and it's actually one of the world's oldest formal methods. Based on set theory and first-order predicate logic, some things that you learned in CS461. It's probably the most widely known and has a variety of resources associated with it. It can also be used in industrial applications, so that's the reason we select that one. Plus, you've probably seen things like Hurrell state charts, which may be more popular and come close to formal methods. That's the reason I select Z. It is probably the most popular one. So, here's a cynical guide to research in formal methods. If you take a look at some of these and take a look at some of the literature, you'll probably notice some patterns. The general idea is that people tend to create formal methods that are moderately different from all the others. They show that it's equivalent to a Turing machine for purposes of computation. That gets you a research paper. They claim that theirs is the best and easiest to use, so you can basically deride the other formal method researchers, and then publish papers where they employ their formal method to create specifications for trivial or abstract systems. Favorite target for this is using a formal method to specify library systems. That'll get you a master's thesis. And then oftentimes the master's students will construct difficult-to-use tools describing the specifications. You get your graduate degree, and you repeat if necessary. If you're looking for a graduate research topic, this line of research may be interesting to you, but we're going to focus just on one of the existing ones, in particular Z. Getting people to use your formal method is a bit harder. In practice, the B method seems to be the only one that's used in industrial practice, which is in some ways close to Z. And if you decide the Hurrell state charts are actually a formal method, then those would probably be the most widely used. If you're interested in Sommerville's take on formal methods, you can look at Web Chapter 27, which is a free chapter on the website. And it is really hard to sell these things. So types of formal methods, I did mention that there's a lot of research in here with people developing them. The virtual library on formal methods at Oxford actually has over 100 different types of formal methods. So here's a brief list of some of the bigger players in the field. There's Z, B, Formalware, Abstract State Machines, SDL, Selection Resolution, Higher Order Logic, and David Hurrell's State Machines. So what does Sommerville have to say about this? And again, you can refer to Web Chapter 27, which is a free chapter located on his website if you want to read the entire thing, but I'll give you a high-level overview. Sommerville basically says formal methods include the specification, the analysis, and the proof, so it is actually possible to mathematically prove these things, transformational development, and the program verification itself. So basically you can prove program correctness. You can prove that a program does what it's supposed to do, or prove that a specification meets the requirements. So why aren't these things more accepted? Formal methods have not become mainstream, and was once predicted that they would, and about 4 different reasons for this. One, other software engineering techniques have been successful in increasing system quality. So the need for formal methods have been reduced. market changes, in particularly time to market, concept to customer, with a low error count is the key factor. Formal methods generally have not been successful in reducing the time to market. And the scope of formal methods is limited. They're not well suited to specifying and analyzing user interfaces, user interaction, real-time systems, video games, etc. And they're still hard to scale up to large systems. So these 4 points are according to Sommerville, and they're fairly accurate. Formal methods do have their proponents in Europe for government projects, and particularly for safety-critical systems, but they've never really garnered wide acceptance in other areas. We'll take a look at a brief sidebar as to the 7 myths of formal methods. And these are from Anthony Hall's 1990 IEEE software article entitled 7 Myths of Formal Methods. So let's take a quick look at these. Okay, myth number 1, formal methods can guarantee that software will be perfect. This is generally propagated by the people who support formal methods. Some things can never be proven, and it's certainly possible to make mistakes in proofs. I probably did it all the time when I was studying mathematics, and I would assume that most people have made a mistake in proving something in math class at some point in time. Formal methods are all about program proving. It's actually more about the specification and doing it rigorously. So thinking about what you're doing before you actually go out and implement it. Myth 3, formal methods are only useful for safety-critical systems. Well, this is the largest application area. Hall did use them for a case tool in his research, but again, I think that was more of a formal exercise. Formal methods require highly trained mathematicians. No, it's quite possible to use Z and to make specifications for systems without being a highly trained mathematician. We won't be doing it this year in 2015, but I have been tremendously successful in getting students to actually be able to specify something using Z. Myth number 5, formal methods increase the cost of development. And again, I think this depends on organizational experience, but if anyone can find some research on this, it would be interesting to see that, to have some empirical evidence versus opinions, either the opinions of myself or Anthony Hall. Myth number 6, formal methods are unacceptable to users. Users might not want to see the mathematical specification, to be honest, but there are other ways of presenting the specification or presenting the interface to user. In general, users and management gloss over the specification document anyway, regardless of what it's written in. You can think back to the train describer system requirements document that we took a look at in CS460. Probably be content with just an executive summary there or seeing the interface. Myth number 7, they're not used on real large software projects. And this one is actually generally true, but there are a couple of counterexamples, and we'll take a look at one of these, and we'll take a look at it. The particular method that was used here was the B method, and the B method was used in a project called Meteor, which was for the line number 14 on the Paris Metro. The project was known as Meteor Project. Don't try Wikipedia for your information here. Wikipedia says that Operation Meteor is the primary device in the Gundam After Colony Alternate Universe. It is a military operation whose original design was the brainchild of Barden Foundation leader Deccan Barden, but was hijacked by the scientists that created the 5 Gundam mobile suits because the original idea amounted merely to genocide. Wikipedia has actually been updated, but the one from Gundam is still the first link that will appear. So it's actually disambiguated now, but it was pretty funny when students looked it up a few years ago. So what is B? It's a formal method, again, developed by the same person who developed Z, Jean-Raymond Abriel, and it's primarily designed to be used in development of industrial applications. It's focused on the development of program code from specifications given in abstract machine notation. So The project description was to make this driverless train for the Paris Metro. And the system consisted of four main components. The PA-SIG-2, which was the automatic pilot and signaling system. That was the safety critical portion where they really focused on the formal methods. The operation control center, platform doors, audio-visual system, and basically what the authors did was they divided it into safety critical and non-safety critical aspects. For example, the audio-visual system would probably be non-safety critical. So you have your safety critical software, your non-safety critical software, and the basic level you have hard-soft interface design, the real-time kernel, and the communication software that make up the safety critical software. So the process they used is they did this in two main phases. One was the modularization phase, basically making an abstract model of the requirements and then transforming it into a concrete one during the design phase. So in a little more detail, they basically did this a little bit differently than the traditional development model. In fact, they did no unit or integration test. The B language took the place of the design document, so there wasn't a requirement document or a functional specification. So they started with a requirement document and made an abstract model in the B language, proved that this worked in the B0 language, and then implemented the source code in Ada, and then did complete functional tests. So they did do functional tests, but they didn't do the unit or integration test, and they did do a requirements document, but they didn't do a functional specification. So here were the validation tasks that they performed. They verified the abstract B model, the interfaces between the B models and the portions that were developed using conventional methods. They validated the mathematical rules, translation of the source code into Ada, and functional tests based on validation. So about 75% of the theorems were actually proven automatically, so it wasn't a theorem proving exercise. They do have automated theorem proving tools, and for these types of things you can oftentimes automatically prove the theorems and prove the specifications automatically. So there were actually really good results from this Meteor project. They didn't find any bugs in the testing process. The integration validation on the target computer, they found no bugs. On-site tests, no bugs. And since the operation in line, there have been no bugs that have been found. So basically the Meteor project was good in showing that formal development and validation processes can be used, and they actually managed to keep things within the initial budget and timing as well. It did require a lot of preparation and efficient methodological guidelines and a continuous improvement of their toolkit, in particular the translation and the theorem proving aspects of it. So let's take a look at the myths again and re-examine a few of them in regard to the success of the Meteor project. Myth number 7 says that they're inefficient. This one was actually efficient. It came in on time and budget, and they actually did have a some non-experts in there. So, and the complete proof of the software was feasible in this case. So myth number 1 may be true, and formal development was actually cost effective in this case. So in summary, Meteor was successful, and so you can actually use these for safety critical projects, and they are very useful in that regard. Now if you're making a video game, these are probably the inappropriate choices to make for developing a video game or for actually developing an application. Meteor was not just a case of exploring the semantics of a programming language or a theoretical exercise, and you can really ride this metro line in Paris, so it is a real-world example. So we'll go back to Sommerville for a few minutes to summarize things, and again I want to re-emphasize that formal methods are not a silver bullet. You need to be aware that they exist. You need to be aware that they are actually very, very useful for safety critical systems. Basically, it involves investing more effort in the early phases of the software development. This reduces requirement errors, and it forces a very detailed analysis of the requirements. Incompleteness and inconsistencies in those requirements can be discovered and resolved through the proving process. And so the savings are made in the amount of rework due to requirement problems, which you'll recall from CS460 can be up to 100 times as expensive as doing fixing implementation problems. So basically what you're doing is you're shifting the cost to the beginning of the software process versus putting them at the end near testing. So, in practice, most proposed changes to the software development process involve shifting costs. Where do you put them? Do you put them at the beginning of the process, or do you put them at the end? Something always has to go first, something always has to go last, so there really isn't a silver bullet. Sommerville talks about two different types of techniques. One is algebraic specification, which describes the system in terms of its operations or relationships. For example, an OBJ or Larch. Model-based specification is used in Z or B, and basically model the system in terms of its states and set sequences. Subsystem interface specification is particularly well suited to this algebraic specification we talked about, and you can decompose a large system into smaller subtypes and specify the interface. This approach works well with specifying classes and abstract data types. 4 parts to it: introduction, description, operation signatures, and the axioms defining the various operations. So here's an example from Sommerville, and this is figure 27.7 from the web chapter 27 in the 9th edition. If you have an 8th edition of the book, it's in on page 225. And this is an algebraic specification for a linked list, which you may remember from 151. Basically, you define your axioms that apply to the abstract data type, and those axioms will specify the semantics for the data type. You define the axioms using the operations defined in the signature part, which you can see down at the bottom, and they specify the semantics by setting out what is always true about the behavior of the entities with that abstract type. Sommerville actually shows that you can use this algebraic specification to work through an example with a linked list. And if you examine it closely, you'll see that you have head, tail, and cons. Cons stands for construct, which means to construct a list from its basic elements. And it looks like somebody may be planning on using list for scheme for this. So next time we're actually going to take a look at how Z works, and what I'd like you to do is in the syllabus, I mentioned the Spivey text and where you can actually find it. I'd like you to take a look at chapter 1 of that. It's going to walk us through an example of how you do a specification using Z.